But processes that would be allowed by the first law of thermodynamics do not happen. So for example, why not have energy move from this one to this one, where the cold gets colder and the hot gets hotter, right? Why not? I mean, transfer 623 joules from this one to this one instead of the other way. It does not happen. For example, if you, I think he talked about, if you throw something on a table due to friction, so it started with some kinetic energy, but now it doesn't have kinetic energy, but because of friction, the table gets hot because of the friction. But you never see the table get cooler, and then these pieces of paper, they gain speed, and then they start moving. It doesn't happen. And even though it doesn't violate conservation of energy, right? I mean, the table can get cooler, lose a little bit of heat, and this one gains that in the form of kinetic energy and then moves. It does not happen. He talked about also the Joule experiment, where you started with a mass on a pulley at a certain height. The mass drops, there are puddles, they stir the water gets hotter, the mass loses potential energy, and then it goes down. But it never happens that the water now starts to get cooler and the mass starts to climb up, get back its own energy. That does not happen. And so a lot of processes don't happen, and how would you quantify that and rule them out? Turns out it's a lot of probability in it, and then it's related to this. So it's called entropy here, and we're going to talk about entropy now. So there are two approaches. There is the probability approach, and then we can talk about the second law of thermodynamics in terms of a form that's more useful for us to calculate this. I will start with quantifying it and learning how to use this new quantity called entropy. Right? I will start by quantifying it and learning how to use this new form called quantity. So it says here, the idea behind the second law of thermodynamics is that energy always goes in a direction where it spreads. Instead of having energy being focused on one spot, it spreads out, it evens out. So here, it was focused, you had more energy here, less here, but at the end, when you reach equilibrium, spontaneously, it spreads out. It spreads out. So, I would just write down the formal statement of the second law of thermodynamics, or read it. It says, and then I would write it probably. The entropy of an isolated system, isolated, has to be isolated, or a group of systems never decreases. It says this quantity called entropy, it never decreases, okay? It either increases until the system reaches equilibrium, and then once the system reaches equilibrium, entropy would stay constant. It does not change, okay? Never the other way. Now, we'll see in the next chapter, when we do refrigerators and so on, with a refrigerator, you can have a cold, the room is cold, but you can still cool it some more. You can take heat out of this room, dump it to the outside when it's hot. Say it's 110 degrees outside. And then the room here is 60 Fahrenheit. But you still can cool the room and make the outside hot. But the key word is spontaneously. It doesn't happen spontaneously. You need a pump somewhere that has to do that. Some work that has to be done to make this room cooler than the outside. Otherwise, if you turn off the AC, what happens to the room? It starts to get warm, it reaches equilibrium. Or if it's already cooler outside, it gets cooler here, so heat flows from here to the outside. So you have to always pay attention to the words. It's an isolated system. And so the second law basically tries to tell you what can happen spontaneously and what does not happen, what processes are possible and which ones are not possible. So let's write down a couple of things. So we're almost there towards the end of this chapter. Well, a few examples to get comfortable with this entropy. And yeah, so. And the second law of thermodynamics. So the entropy of an isolated system or group of systems never decreases, and the entropy either increases until the system reaches equilibrium or it just stays the same. So, the entropy of an isolated system never decreases. Again, the key word is isolated. It either increases until equilibrium is reached or stays the same. Stays the same. So it tells us what processes can happen and what processes do not happen. An informal statement. There are many statements of the second law of thermodynamics. One of them is heat never flows spontaneously from cold to hot. It flows spontaneously from hot to cold. So that's one of them. Another one, it says the direction of time in which entropy of an isolated macroscopic system increases is the future. So let's say you're watching a video run backward. How do you know that the video is actually playing backward?
The motion?
Yeah, and then the motion, and then you see things that shouldn't happen. Let's say you have an egg that falls, it breaks, and then if the video is playing backward, the egg kind of comes back and then becomes an egg. So you know it's playing backward. So it says the direction of the future is the direction where the entropy is increasing. So figure out if the entropy is increasing, then that is the future. But if the video is playing backward, you will find that the entropy will be decreasing. And then, so you know that that's not the future. That's probably the past. That's an informal statement also. Okay, so again, I will skip the statistical interpretation at the moment. Maybe we'll touch on it next time, or maybe in a worksheet or something. But for now, I want to give entropy a symbol and then be able to calculate it. So entropy, S stands for entropy. S stands for entropy. Let's see. The units of entropy will be joules per Kelvin. Joules per Kelvin. And for a quasi-static process, meaning the process is always near equilibrium. So for a quasi-static, meaning almost static, quasi-static process, ds will equal to dq divided by d. So this applies for a quasi-static. So quasi-static is like, you can have equilibrium and then nothing changes. Quasi-static, you want to have it both ways. You want it to change, but not too fast. Because if the change is sudden, then this is not true. So for example, if you have, we'll deal with an example where you have a gas on one barrier, on one side, and then you break let's say you cut the curtain, and then the gas molecules spread out, that's not a quasi-static process. It's called an irreversible process. Okay. So how do I calculate it? So first of all, in accordance to the second law of thermodynamics, it says delta S for an isolated system. For an isolated system is always greater or equal to 0, right? That's what it says. It's always increasing, never decreases. So the change in entropy should always be greater or equal to 0. The equality happens when the process is reversible. Okay? So at equilibrium, nothing is changing, and you get change in entropy would be 0, right? At equilibrium, change in entropy would be 0. Okay, so let's get our first practice to calculate entropy for an isothermal process. That's probably the easiest process. And the reason is, I mean, you see here, you get a differential here, ds, and to get delta S, you have to integrate, right? You have to integrate. And to integrate, I have here dq over t. So I have to figure out how dq depends on t to be able to evaluate this entropy. So let's do the first one is isothermal process. We're trying to figure out how to calculate the entropy for different processes. Let's do the first one for an isothermal process. Isothermal process means the temperature is constant. So I will start with here, ds is equal to dq over t. I integrate both sides, so I get delta S, right? Change in entropy. So this is dq over t. Now, if the temperature is constant, 1 over t comes out of the integral, doesn't it? It's constant. 1 over t dq. And if you integrate dq, that's the total heat that you have added to your system. So it's just heat. So for an isothermal process, delta S is equal to just q over t. This is isothermal. For example, here's an isothermal process. When ice at 0 degrees Celsius, melts and becomes water at 0 degrees Celsius, the temperature is constant, but there is heat added. Right? Oh, I should have said this is heat, right? Q, I think, stands for heat, and this is temperature. And it's in kelvins. And so the units of entropy, by the way, would be units of heat divided by temperature. What are the units of heat? Joules. Units of temperature?
Kelvin.
Kelvin, so joules per Kelvin, yeah.
Is it just a coincidence that the Boltzmann constant has the same units?
No. No.
So that's also related to
It's KB times the natural log of the number of states. So that's the statistical interpretation of it, yeah. So it's not a coincidence, no. Yeah. So I think there is a decent discussion in the book, so read that. I'm not going to probably test you on anything that has to do with the statistical interpretation. We want to do the calculations. Yeah. So let's do an example here. Let's say you have water or ice. 100 grams of ice melts. 100 grams of ice. So here is an example. 100 grams of ice at 0 degrees Celsius become 100 grams of water at 0 degrees Celsius. Okay? Does this process happen spontaneously or no?
No.
So if you, let's say you leave ice at 0 degrees,
Oh.
it becomes water at 0 degrees, right?
Right.
Does it happen the other way?
No.
Like you leave water at 0 degrees and then by itself, it will lose heat to the environment and then it becomes ice. No, that doesn't happen. So since this future, this is the future, the change in entropy should be positive or not positive?
Positive.
Be positive, yes. It's a spontaneous process, so it will happen. And to do this calculation, by the way, here is the latent heat of fusion is 3.33 times 10 to the 5th joules per kilogram. Right? So now, let's see. This is an isothermal process because the temperature has not changed. It's 0 degrees Celsius. In fact, we have to change it to Kelvin, so it's 273 Kelvin, right? It starts at 273 Kelvin and ends at 273 Kelvin while the ice is melting. So, solution. We will just use this. So I know that's delta S. Equal to Q over the temperature. Now, the temperature is, or before I substitute, what is Q? How much heat needs to be absorbed? How do I calculate the heat? It was in the quiz, right? Similar.
NCV.
M.
L of F.
Yeah, the mass of the sample times the latent heat of fusion divided by the temperature. That's the heat needed for melting. So you get, the mass is 100 grams, so 0.1, 3.33 times 10 to the 5th over the temperature, which is 273 Kelvin, right? Temperature should be in Kelvin. And, yeah, you have to be in Kelvin. Otherwise, you'll be divided by 0, right? And so, I think I get 122.
Yeah.
122, okay. 122 joules per K. Joules per K. So that's the first process. And yeah.
Oh, can you go over like the beginning of the example again? Like before we wrote the latent heat?
So from the beginning?
Yeah.
Oh yeah, so the setup of this example is, suppose you have 100 grams of ice at 0 degrees Celsius. And they melt, and they become 100 grams of water at 0 degrees Celsius. And the question was, what's the change in entropy? What is the change in entropy? So I said, they start at 0 when it's always 0, right? So the process is isothermal. Since it's isothermal, I can use this formula. I mean, technically, I have to always integrate, but since the temperature is constant, it ends up being this. So it's the heat divided by the temperature at which the heat is added. Now the temperature is always 273, so that's the bottom. Now how much heat needs to be added? That's the heat needed to melt the ice. And it is related to the mass of the ice times the latent heat of fusion. Okay. So, yeah, does that answer?
Yeah, thank you.
Now the next one is, how about if the temperature is changing? What if the temperature is changing? What do I do? Well, it depends on how the temperature changes. Okay? So the next one is let's say I have now, let's say the ice melted. It became water at 0 degrees. I add heat. As I add heat, what happens to the temperature?
Rises.
Rises. Do I know the relationship between temperature rising and heat added? For water, let's say, or a solid.
Is the delta T, sir?
Yeah, it's the, let me, entropy of heating. So now let's say the temperature changes. So the temperature is not constant. So let's say I start with my sample of water and I heat it. It stays water, let's say it's at 0 degrees, I heat it to 70. And the question is, what's the change in entropy? So in that case, I have delta S is equal to the integral of dq over t, right? Now what is dq? Well, if you have a sample of water and the temperature is changing, it's mc delta t, and if I'm talking about dq, it would be mc dt. So it would be the mass of the sample times the specific heat times dt over t. Yeah.
In this case, the specific heat is just C, right? It's not CV or CP.
This is, yeah, it's, for a gas, we would have to be more specific whether it's
Oh, okay.
CV or CP. But this one is just a, let's say a solid or a liquid that's
Okay.
not changing phase.
Okay, got it.
Yeah.
Thank you.
So, I thought I saw a hand. So suppose again, you have water, let's say at 0 degrees, and you add heat to it, it becomes water at 20 degrees. How much did the entropy change? What is the entropy change? So that's what we do to calculate this. So you integrate from the initial temperature to the final temperature. Okay? And so you would have MC. MC is a constant. So what's the antiderivative of 1 over t?
Natural log.
Natural log of t. And then so you have natural log at t final minus the natural log at t initial. And we encountered that several times. So it's t final over t initial, right? So that's another calculation of entropy. So let's do an example. Here's the example. Let's say I have my water now at 0 degrees. To what temperature do I need to heat the water? So I started with 100 grams of ice. At 0, they became 100 grams of water at 0, and that increased the temperature by increased the entropy by 122 joules per Kelvin. Okay. Now, starting with 100 grams of water. Example. So let's say I have 100 grams of water at 0 degrees Celsius to 100 grams of water at some T final. The question is, what should T final be so that the change in entropy will be 122? So, find T final if the change in entropy is 122. Okay. Well, in this case, we know the left side. The change in entropy is given, it's 122. And I'm looking for the right side. Right side. So let me change this a little bit. I keep looking at the time to make sure that I finish on time. So, this is the process that's exactly described by this equation, so I will use this equation. So I have this, delta S is equal to M C natural log T final over T initial. Delta S is what again? 122. Let's see on the right hand side, what is the mass?
100.
100 grams, so 0.1 kilograms, right? 0.1 kilograms. What is the specific heat of water?
4190.
Yeah, good. Good memory. 4,190. 4190. 4,190. This will be given to you, of course, if it's a quiz or something. Yeah, so 4190, C for water. This is the mass. This is C. And then the natural log of T final over T initial. What's the initial temperature?
Zero.
Or zero.
273.
But it's 273 in K, right? 273. Can we solve this? Yes, we could. We have to divide by this, and then do e to the to cancel the natural log, and then solve for T final. So if we do that, let's do 122 over 0.1 times this 4190. So that will be 122 over 419, right? So 0.1 times this, we get 419. So 122 over 419. I don't have a calculator with me. Someone can help me. What is 122 over 419? I'm sorry?
0.291.
0.291 is equal to ln of T final over 273. And so do e to both sides, so e to the 0.291 is equal to T final over 273. And so T final will be, so e to this times 273 will give you a T final of 365.
365.21.
About
365.21.
so 365 kelvins, and in degrees Celsius,
Kelvin. And it's just
92.2.
92.2.
so subtract 273, so 92 you said?
Yeah.
Yeah, about 92 myself. So 92 point something probably. So 92 is good enough. Alright. Yeah, so that's that. I mean, the problem can be made a little bit more complicated than this. For example, let's say they say, to what temperature should water be heated until the change in entropy is, let's say, 200. In that case, you can assume it's still liquid water, but then you will find that the temperature is higher than 100. So you realize that the water started to boil, and you have to use steam, and you can find out that way. Yeah. All right. How about ideal gases? What's their entropy? Well, for an ideal gas, you can have different processes also. Right? So for ideal gases, let's see. So I know that dE thermal is equal to dQ plus d double, right? E is Q plus W. In differential form, I have it. And so dQ will equal to dE thermal minus d double. Right? Now, what is dE thermal? Or what is E thermal for an ideal gas? I think you said it at the very beginning.
And
3/2.
Oh, the 3/2 and NKBT, but that becomes NRT?
3/2. It was N CV DT, right?
Oh, yeah, okay.
Yeah. So 3/2 NRT, but CV is 3/2 R, right? For an ideal monatomic gas. But for now, let me leave it general, just with CV, to also include something that is not monatomic. So I have this dQ. So dE will be N CV dt. That's dE. Okay. Minus dW, remember dW is negative P dV?
Mhm.
dW is negative P dV, so it's minus P dV. So it becomes a plus, minus minus becomes a plus. So dQ is equal to N CV dt plus P dV. But what's P?
Pressure.
Yeah, and it is nRT over V.
Over V.
Over V, yes, nRT over V, right? That's the pressure. And I have used the ideal gas law, in other words, right? Okay. So that's dQ. So now, ds is dQ over T. So let's divide this is dQ. Right? dQ is all this now. Divide that by T and see what's equal. So you get N CV and then dt over T plus, what happens here when I divide by T?
T cancels
This
out.
The T cancels, good. So I get NR and then dV over V. NR dV over V. So let's integrate this to get delta S. Delta S will be N CV. The integral of 1 over T is ln of T. So between T initial and T final, we get ln of T final over T initial. ln T final over T initial plus NR. Integral of 1 over V again, or dV over V would give me ln of V. And between V initial and V final, I get ln of V final over V initial. Like this, right? So, any restriction on this for what process it works or for what process it doesn't work? Did we impose any restriction?
Would have to be no.
We did not mention any restriction. So this applies for any ideal gas process. So let's try to see what special cases we get. So this is the entropy. But let's again make sure you have this form. Let's say you're taking your notes, right? Then you have a quiz, and then you see what's the change in entropy, and then you have a solid or a liquid, and then you try to apply this. That'll be wrong, because this is for an ideal gas process. Solid or a liquid, you probably will go here. Okay? So make sure you remember under what circumstances a formula is derived, and for what it applies. So, okay. So let's see, for an isoporic process, what do I get? What does this boil down to? If isoporic volume is the same, there is no change. So V final over V initial would be would be 1, right? If the volume doesn't change, the final divided by the initial would be 1. What's the natural log of 1?
0.
0. So you just end up with this. So let's write it. So for an isoporic, you end up with delta S is equal to N CV natural log T final over T initial. Right, let's do isobaric. Think about how an isobaric process looks like. What would we get? For an isobaric process, what does it become? Well, isobaric means the pressure is the same. So let me write down the ideal gas law twice. So we know that P initial, V initial is equal to N R T initial, right? And P final, V final is equal to N R T final. Now, if the pressure is constant, the P initial is equal to P final because it's isobaric. So divide the two equations, you get P final over P initial, right? This over that. The NR is cancelled, and you get V final over V initial. Isn't it? So V final over V initial is the same as T final over V initial. So let's look at this formula now, what it becomes. So I have T final over T initial, but this V final over V initial can be written as what? T final over T initial. And see where it takes us. So again, delta S would be NCV, natural log T final over T initial plus NR, and then natural log of T final over T initial. Again, NR, it used to be natural log of V final over V initial, but for an isobaric process, V final over V initial is the same as T final over T initial. What's the advantage of writing everything in T final? Well, I have T final and T initial. The two terms here, they look alike. And see, let's see where this takes us. Let's factor the N out, and let's also factor the natural log of T final over T initial. What is left? CV
CV plus R.
plus R, yeah. And what is CV plus R?
CP.
Yes, CP is CV plus R. So we end up with, for an isobaric process, delta S is equal to N CP times the natural log of T final T initial. And I put a box around it. This is, but again, if you, let's say you look in your notes and you find a formula and then you try to plug in the numbers, you have to figure out under what circumstances it applies. So this one applies for an ideal gas at constant pressure, process related constant pressure. Okay. So, any question on this one? Yeah.
So then you could also say delta S is NCP, natural log of T over.
Yes.
Okay.
Because they're the same. Yeah, if you're given the volume, there is no reason to go and calculate temperatures, only to plug in the same thing. Yeah, good. I think you had
It was the same question.
it was the same question. Yeah. How about the end there? Did you guys have a question or? Yeah.
You said that entropy can be negative, right?
No.
Oh, no.
No. Well, okay. If you have another process involved, it could be negative for one part of the system, but then positive on the other parts. But once you add the whole thing, it is either 0 or greater than 0. Yeah.
Because I think I misunderstood you, and like, because when you said like something about entropy having like a negative number,
Yeah.
or like entropy